Welcome to our video, where we explore the exciting world of artificial intelligence. Monte Carlo techniques are a class of computational methods that rely on random sampling to solve complex problems in science, engineering, finance, and other fields. The term Monte Carlo refers to the famous casino in Monaco, which is known for its gambling and games of chance. Monte Carlo techniques are based on the idea of simulating random events, using statistical methods to analyze the results, and using the insights gained to make predictions or solve problems. The origins of Monte Carlo techniques can be traced back to the work of Stanislaw Ulam and Nicholas Metropolis in the 1940s, who were working on the Manhattan Project and needed a way to simulate the behavior of neutrons in a nuclear reactor. They realized that they could use random numbers to simulate the random motion of the neutrons and estimate the probability of various outcomes. Since then, Monte Carlo techniques have been applied to a wide range of problems, including optimization, finance, physics, chemistry, biology, and more. In this article, we will explore the basics of Monte Carlo techniques, how they work, and some common applications. Basic concepts of Monte Carlo techniques. Monte Carlo techniques are based on the idea of using random sampling to simulate a complex system and estimate the behavior of the system. The key steps in a Monte Carlo simulation are as follows. Define the problem. The first step in a Monte Carlo simulation is to define the problem you want to solve. This could be anything from estimating the value of pi to simulating the behavior of a complex financial system. Generate random numbers. The next step is to generate random numbers that will be used to simulate the system. These random numbers can be generated using various methods, such as a random number generator or a physical process that produces random results. Simulate the system. Once you have generated the random numbers, you can use them to simulate the system you are interested in. This could involve simulating the motion of particles in a physical system, the behavior of a financial market, or the performance of a complex algorithm. Analyze the results. After simulating the system, you can analyze the results to estimate the behavior of the system. This could involve calculating the mean, variance, or other statistical measures of the data. Refine the model. If the results are not accurate enough, you can refine the model by adjusting the parameters of the simulation or using a more sophisticated algorithm. Monte Carlo techniques can be used for both deterministic and stochastic problems. Deterministic problems are those where the outcome is entirely predictable based on the input data, while stochastic problems are those where the outcome is random or uncertain. Monte Carlo techniques are particularly useful for stochastic problems, as they can generate a large number of random samples and analyze the results to estimate the behavior of the system. How Monte Carlo techniques work. Monte Carlo techniques are based on the principle of statistical inference, which is the process of making inferences about a population based on a sample of data. In a Monte Carlo simulation, the population is the complex system you are interested in, and the sample is the set of random numbers that you use to simulate the system. The basic idea behind Monte Carlo techniques is that if you generate enough random samples and analyze the results, you can estimate the behavior of the system with a high degree of accuracy. The accuracy of the estimate depends on the number of random samples you generate, the quality of the random number generator, and the complexity of the system you are simulating. Monte Carlo techniques can be used for a wide range of applications, including optimization, simulation, and statistical analysis. Some common applications of Monte Carlo techniques include option pricing. Monte Carlo techniques are often used in finance to price options and other financial instruments. The basic idea is to simulate the price of the underlying asset using a stochastic process, such as geometric Brownian motion, and use the results to estimate the value of the option. Risk analysis. Monte Carlo techniques can be used to estimate the risk associated with a particular investment or project. By simulating the cash flows and other relevant factors using random sampling, you can estimate the probability of different outcomes and identify the most likely risks. Image processing. Monte Carlo techniques can be used to process and analyze images, such as in medical imaging or satellite imaging. By simulating the noise and other factors that affect the image, you can improve the accuracy and quality of the image. Particle physics. Monte Carlo techniques are used extensively in particle physics to simulate the behavior of particles and estimate the outcomes of experiments. By simulating the random interactions between particles, physicists can test theories and make predictions about the behavior of the universe. Monte Carlo techniques are not without limitations, however. One of the biggest challenges in Monte Carlo simulations is generating high-quality random numbers. If the random numbers are not truly random or do not have the appropriate statistical properties, the results of the simulation may be inaccurate or biased. Additionally, Monte Carlo simulations can be computationally expensive, particularly if a large number of random samples are required to obtain accurate results. Applications of Monte Carlo techniques. Monte Carlo techniques are used in a wide range of fields, including finance, engineering, physics, chemistry, biology, and more. In this section, we will explore some common applications of Monte Carlo techniques in different fields. Finance. Monte Carlo techniques are widely used in finance for a variety of purposes, including option pricing, risk analysis, and portfolio optimization. In option pricing, Monte Carlo simulations are used to estimate the value of options and other financial derivatives. By simulating the price of the underlying asset using a stochastic process and using the results to estimate the value of the option, traders and investors can make informed decisions about whether to buy or sell the option. In risk analysis, Monte Carlo simulations are used to estimate the risk associated with different investments or projects. By simulating the cash flows and other relevant factors using random sampling, analysts can estimate the probability of different outcomes and identify the most likely risks. This can help investors and managers make informed decisions about how to allocate resources and manage risk. Engineering. Monte Carlo techniques are also widely used in engineering for a variety of purposes, including design optimization, reliability analysis, and simulation. In design optimization, Monte Carlo simulations are used to explore different design options and identify the optimal design that meets the desired performance criteria. By simulating the performance of different design options using random sampling, engineers can identify the design that maximizes performance while minimizing cost. In reliability analysis, Monte Carlo simulations are used to estimate the reliability of complex systems and identify potential failure modes. By simulating the performance of different components using random sampling, engineers can estimate the probability of failure and identify the most critical components that need to be improved. Physics. Monte Carlo techniques are widely used in physics for a variety of purposes, including particle physics, astrophysics, and condensed matter physics. In particle physics, Monte Carlo simulations are used to simulate the behavior of particles and estimate the outcomes of experiments. By simulating the random interactions between particles, physicists can test theories and make predictions about the behavior of the universe. In astrophysics, Monte Carlo techniques are used to simulate the behavior of stars, galaxies, and other celestial objects. By simulating the random interactions between particles and other factors that affect the behavior of these objects, astrophysicists can make predictions about their behavior and understand the underlying physics. Biology. Monte Carlo techniques are also used in biology for a variety of purposes, including drug discovery, protein folding, and population genetics. In drug discovery, Monte Carlo simulations are used to simulate the behavior of potential drug molecules and identify those with the greatest potential for success. By simulating the behavior of these molecules using random sampling, researchers can identify those that are most likely to be effective and safe. In protein folding, Monte Carlo simulations are used to simulate the folding of proteins and understand the underlying physics. By simulating the behavior of these proteins using random sampling, researchers can understand the factors that affect protein folding and develop new drugs that target specific proteins. By simulating the behavior of these populations using random sampling, researchers can understand the factors that affect the genetic makeup of a population and develop strategies to improve genetic diversity. Monte Carlo techniques are a powerful tool for simulating complex systems and estimating the behavior of these systems. They are used in a wide range of fields, including finance, engineering, physics, chemistry, biology, and more. By simulating the behavior of these systems using random sampling, researchers can identify the most likely outcomes, estimate the risk associated with different investments or projects, and develop new materials and drugs with desired properties. While Monte Carlo simulations have their limitations, they remain an important tool for scientific research and practical applications.